Okay, that's fine then. So, good morning, everybody. Now it's X-rays because now we are looking for single crystal X-ray crystallography, and of course we have to develop all these things from the bottom to the end to the real life, and then finally you will be able to work with these things, and you can solve their structures by yourself and visualize and do these things. But we have to develop the theory first in order to understand what we are doing. So there is virtually no mathematics, but this is good in that sense because the computer is doing all the homework, the handwork, so we don't have to really go deep in the mathematical theory. But I will try to explain in spoken words some of the important points which we will be facing, which we have to understand. So the point in there is that all these things can be mathematically shown, but the actual idea is really to understand these things. When you do the work, you don't see what is happening. You see only the result. But then it's very important to understand where does the result come from. And we were looking yesterday, the first important thing, which was the X-rays. So how to make X-rays and which device is used to make them, and then we can make them monochromatic. We know the wavelength of these is very important for the Bragg's law. And then we develop this even further. So we go step by step, starting from really, like, let's then move more and more. So we go more from theory to the practice at the later part of the course. So the point we will discuss that now in this first course, Bragg's law, crystals, lattices, unite cells, crystal systems, and coordinates. So these are all these things which actually come from the diffraction itself, but that's how it goes. So the important point is, remember, we have always discussed that the X-rays are light of a certain kind of a light with a certain wavelength, but behaves like a wave. And this wave is very important. So here you can see waves, and now you can see that every sixth of this wave will go inside, and then if we measure this point from that point, we can call it, that's the lambda, that's the wavelength. And the idea is that we can have waves, several waves going the same direction at the same time, and this is important for diffraction. So the point is, consider wave 1 here, and then you have wave 2, and now the point in there is that if they are in the same phase, so meaning that now the maximum of this interlap, then we call it as a constructive interference. So these two waves, in a sense, like sum up to make a stronger wave. And this is really important for us because if we look at that, here we have, in this ways, we speak about, let's consider that there is an imaginary plane here, and then the wave 1 hits there and diffracts. This we know from the Bragg's law already here, how it diffracts, because now we know, we defined our X-rays, we know the wavelength, and then we can measure this theta angle, then we can measure the distance between these two planes. But the point, in order this diffraction to happen, there has to be a constructive interference. And this constructive interference can only happen if these are in the same phase. So if these wave 1 and 2 would be in a different phase, they will cancel, otherwise we would see nothing. So that is very important, that we can get that the coming waves are in the same phase, and then only then we have the diffraction happening. So this is in principle the idea, how you can coin, or actually mathematically coin, the Bragg's law. But the point in there is not very important for us because this is automatically embedded in the computer programs, so we don't have to worry about it too much. But then there are also other things, because now you can consider that the phases are, so we can have the n different in the Bragg's law. I go backwards in, so there's always this n here. So n lambda. No, typically in our case, n is always 1. We are not so concerned about the higher order reflections, but that's the idea. We call it harmonic series of planes in that sense. But in principle, the same applies here. So this is the actual audio. And now the d here is the distance between these, what we now later will call planes, where the diffraction happens. And now you will see a very strange nomenclature here like HKL. Don't worry about this yet, because these things has to be treated in this time before going in the definition. What is this HKL? What does it mean? But we will go into it. But we consider that this is now, the HKL is an entity where the diffraction happens, and the d is the distance on individual HKLs. And then this n can change 1, 2, 3, and 4. Us, as I pointed out to you earlier, we are only concerned the number 1. We don't have to worry about this anywhere anyways. So the point is there that we can consider that, okay, this is a little bit too much for you at this moment, but we don't consider the second order diffractions because it was not helpful for us at all. And it's a pity in that sense, because this slide should be later, but we have to go this through before we can move forward. So don't worry about these numbers. What is this 1, 2, 1, 1, and so on? What is a lattice plane? It will come just later on. But this is just an idea. You can return back to the higher order of diffraction if you are interested after it has been dealt what this HKL and the planes mean. So the point here, there is a small mathematical calculation. What does it mean? That if the d is, we know the d, and then n is either 1 or 2, and lambda is known, we can calculate where the diffraction is happening. So the idea, what we can get there is a diffraction angle. So this is direct consequence from the Bragg's law, that if the distance of the entities or planes where the diffraction happens, if this is known, we can calculate where it happens. What is the direction for this diffraction? But on the other way around, if we know the angle, we can then calculate the d. So that is the only essence for this kind of a thing. It's a very simple mathematical formulation. It's nothing very complex, but there's a lot of additional things which are associated with this diffraction. But this is just mathematics. We don't have to know anything what is there which is causing the diffraction. We can calculate if there is a diffraction where it happens. That's the point in here. And now the idea is that we can then calculate, based on this, we can calculate the maximum number of these. So we call, this is interesting in that sense, that we call it diffraction. So the phenomena is diffraction, but we call that diffracted beam as a reflection. So this is a little bit misleading in that sense, but the phenomena is diffraction, but what comes out from there is reflection. And that's what we call the reflection. So we can calculate how many reflections there is possible. Because this how many there are possible of these depends on the distance d, and then the angle. And this is actually what is there. So this says that how one of the Bragg's law, of course, and the idea is used. So when we have in this, don't worry about this yet now. When we have these, that the spacing or the separation of the what we now call diffraction planes gets smaller, the more reflections you get out of it. And based on that, we can calculate, but then there is a practical limit also, which is the limit of the detection. So we cannot detect something which goes backwards. So there is a mechanical limit for then these numbers. And if there is a mechanical limit for these numbers, we can know how many individual reflections there will be, which can come out of there. Again, this is a very abstract at this stage, because later on it will be more practical information why we need this, why this is important, the idea. But the point in there is that the diffraction beam is never more than 90 degrees. So the actual idea is that if the diffraction happens to 90 degrees, that's the absolute maximum. And then, of course, we always use the Bragg's law uses 2 theta. So then we have 180. That reflects that the theta angle is 90. So when we take a wavelength and we use this to maximum resolution, we can calculate what the resolution means, the D's. It means the separation of these planes where the diffraction happens. It has an importance in the later on, you will see this thing, but it's a theoretical figure. We don't have to know anything where the diffraction is happening, but now we can calculate how much information we can get out of this based on individual wavelength. And now you can see here that if we take a copper radiation, based on this calculation, we can see diffraction with the instrument where the separation of these individual planes, where the diffraction happens, is 0.77 angstroms. And if we are using, because the wavelength is 1.5, and now if we use molybdenum radiation, then the resolution is this. And why this is important, why I'm talking about this. Now we come back to the idea that what is there with is causing a diffraction are atoms and molecules, or atoms in molecules. And now the point in there is that this number indicates that how close objects we can separate. And if this is a very long, let's say it's 2 angstroms, we can't see individual atoms. But if it's 0.7, there is no atoms which are closer than 0.7. So the information what we can get there, it is enough. We see all the atoms. That's what it means. As singular atoms in there. We don't see like larger bodies. We see individual atoms. And this is the importance of resolution. And if any of you know anything about the protein X-ray diffraction, they speak about 2 angstrom resolution or 2.5 angstrom resolution. That's the same idea. So the resolution means how close objects we can see with individual radiation. And then if this wavelength gets very long, then the resolution is not suitable for us anymore. That is one of the reasons why we use X-rays. And then copper radiation and molybdenum radiation are these what we are using. But the point, what this leads there now, we will discuss this symmetry of the crystals and later, but it means that how much information we can get out from there. That depends on, later on, again, we can then calculate, but it's from few to thousands or tens of thousands. And that is the mechanical thing what we have to do. We have to be able to measure each and every one of them. Remember, I spoke to you that the diffraction image, each individual spot contains a tiny part of the information. And that's the idea. So diffraction from the power, diffraction power, crystal, and the primary beam, exposure time, all these dictate how high resolution we can reach. But nowadays, this is a typical thing. All the current instruments can reach this level easily, so that's not a big deal. So with the copper radiation, so typically 0.79 or 0.77, actually it's a real number. So currently, so we can reach the theoretical maximum. So this is a theoretical maximum. We can reach this, which means that we can get all the information from the structure which is possible to get. So nothing is hidden. So that is very good for us. But that was actually just an interlude for the diffraction from a crystal. And now we have to go more on what is a crystal and why the diffraction happens and why we call it single crystal X-ray diffraction. And I told you, okay, we spoke about that the name of the course is Supramolecular Crystallography. It doesn't matter what object you are studying. Will it be purely organic, it will be inorganic, or and I will show you an example, a real walkthrough here from a chiral organic molecule. But it can be anything. So it could be a MOF, it could be a polyoxometalate, it could be a metal cluster. It doesn't matter what it is. The only thing is that it has to form a crystal which is ordered. And I touched that briefly already in there, but we later go more in detail and also learn how to grow the crystals and what is the methods to get them done. But the point in there is that there's sometimes controversy of taking about, okay, what is crystalline? And what is, this is a crystal, there is some crystallinity in the system and so on and so on. But in our case, in this course, there is an absolute demand on certain things. It has to be organized in 3 dimensions. And that is a cartoon-like presentation. So here, when we have something, here the black dots are ordered here internally. In now it's 2-dimensional picture, but it has to be 3-dimensionally organized. So if you take any point here, and then you look for the distance to the neighbors, it's always the same. And now this is then crystalline. And if it's like this, then it's a single crystalline. Single crystal means that you have only one ordered entity in there. And then we have another form, which is a very typical. You have seen a lot of these things where there is no order. And when there is no order in the same objects, we call this amorphous. And the direct consequence of these things, because I've already emphasized that the X-rays are diffracting from a periodic 3-dimensional ordered objects, aka these kind of things, then this is not diffracting at all. So we can tell from the X-ray diffraction if our object is crystalline or not. And we can even tell it if it's a single crystalline. That will be later on. And that's the idea. We can then have an additional form which is annoying for us. We call it polycrystalline. So it is like one entity, but it has domains. So here we have one single crystal. Here we have another, but they are in different orientation. It's not the same. So you cannot go from here to here in the same way you can go from here to the next one. And now in here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In here, in this polycrystalline single objects, is actually 12 single crystals. In theory, we can use these kind of materials also, but in practical terms only when we have 2 of them. And then we call it a twin crystal. Twin means a double crystal, but it's physically one object. You cannot see by your eye that it actually consists of 2 crystals. Only the X-rays, only the diffraction can tell you this, but that's the idea. So, and I'm really emphasizing it here that when you are, if you want to do a single crystal X-ray diffraction study on any material, 98% of the case, the most complicated thing is to get the good single crystal. Because if you don't get the good single crystal, you don't get anything. So absolute 0. So that's the idea, that the most difficult aspects of crystallography is obtaining so good quality single crystals. And now you can easily imagine supramolecular chemistry or supramolecular structures or protein structures, any large biology. The larger is the entity, the more difficult it is to organize it in 3 dimensions. So the phenomena that is really organizing in 3 dimensions is a miracle in a certain sense. Because if it doesn't happen, then we have an amorphous system. This is really some kind of intermediate. Normally what we do, and if we find out that our object is like this, we try to do it again that we would have it as a single crystal. That's the idea. So the crystal growth will be discussed later on a bit. on that. But it's also a state of art. It's very difficult to explain how and why the crystallization happens, because the environment, all there's a temperature, pressure, light, even all these things can have a subtle changes there, and this will then lead on the crystal growth or not. And that's really an art, and we can discuss that later on. But the point is how the single crystals or the materials of this type can look. So here, that looks quite good, but you can see that this is very typical. You don't see isolated single crystals. You might see a group of single crystals. So that looks quite fine. At least this part looks okay. Here we have a collection of things not very good looking. This looks partly okay. Here you can see even some colors, but this color is in the surface. So these clear parts in this crystal look to be nice by eye, but it's the diffractometer that tells. This is clearly a class. So this, you would say that just by looking in the microscope, you would say that's amorphous. Here again are rather strange looking, could be single crystals. And in here we have a needle type, could be. Sometimes when you look, there are all microscopic images, and later on you will learn why we need the microscope for this. So you might see two different colors completely, and you can see it's nicely separated that the pink colors are in, the crystals are in this side, and the purple blue colors are in here. This is actually the same crystal, but the orientation of the crystal is different. So you can consider these pink ones are like this, and then the blue ones are like that. And then this is an isotropic in that sense. The color, the wavelength, goes in a different, you get a different wavelength going through of the crystal. So they might look different colored, but it's still the same crystal. It can also happen that we have two different structures, two different crystals. We don't know this before we have done the work. And then you can see here, this is a very nasty looking kind of a thing. There might be some nice looking crystals or whatever. So when you're doing this work, the first critical thing is to make a good crystal, look that through microscope. But now to the real business. So we have to develop a few completely hypothetical concepts which don't exist in real life. This is a really difficult thing. It takes some time. And one of them is crystal lattice. Or if you make it more general, a grid. And the point in the lattice is an abstract mathematical concept describing regular infinite arrangement of points. So here we have points. Now, these black dots are points. So we call that as a lattice point. Why we call it as a lattice point? Because lattice is this, now in this case, two-dimensional repeatable structure which always the points relate to others are the same. So then this is called the grid. And now consider that now these are points, they are completely imaginary. This point, but you can imagine this kind of things existing there. And if that's the case, then it's called a lattice, and this is a lattice point. So lattice is in 2 dimensions. And now when you consider that, okay, your molecules are ordered also there in real life, they are ordered in the way that they are always sitting in the same position. So 1 molecule, 2 molecule, there are 3, 4, and so on. This is a part of that. But now these ellipsoidal are the molecules. But now when you see the molecules behave in the same way as the points here in this lattice. So actually these molecules now create a lattice. But the molecules are physical objects, they are real, but the lattice is not. Lattice is just a construct which is made from the ordered objects. And that is the idea. And then the point, every point in the semi-alignment of any point. And then the point in there is you can select this, how to describe this lattice as you like. And they are a little bit difficult to understand because they are very abstract things. And the repeating motif here can be, of course, single atom, a molecule, or a building block of a network structure. So it could be a moth. So it doesn't matter. But the point in there, and then we normally select an origin for this, for the lattice. And for example, if this is an atom, we can select this is the origin for that. Or it could be an empty point somewhere in the middle. So everything is up to us. We can do the decision as we like. But the only thing is that it has to be repeatable in the 3 dimensions. So all the directions have to look exactly the same. And that's the idea. But the point in there is that this is 2-dimensional. And of course, our life is not 2-dimensional, it's 3-dimensional. So we have to add the 3rd dimension. So it's very easy for us to do. So this first point here is the 2-dimensional. We add now the 3rd dimension on that direction. So we put the same points there, but 1 step further in that direction, and then again. And now this distance here is the same the distance in here, in this case. So by joining now all these points, you can get a box. And now this box is very important for us. Because if you look carefully, this blue box here, you can move it anywhere in here. And it's the same box. But if you repeat this direction, that direction, and that direction long enough, you will get a physical object. So this is the smallest possible repeatable unit which describes the whole object. So we could take like a big box, let's say 1 meter times 1 meter times 1 meter, a cube, and we can slice it to 10 million parts, which are all the same things. It's like a tiny part. Then what we have to do is we just repeat that one little box 10 million times, then we will get the big box. And that's the idea. So this entity we call the unit cell. So the unit cell is the smallest repeatable 3-dimensional part of a real crystal. But the point in there is that this is imaginary. It really doesn't exist unless we define it. And this is also the idea of what we do. So we define ourselves, what is this? But there is an interesting point in here that these things, the shapes of the unit cells and so on, can be mathematically determined without any information what is inside and without these molecules. So we can do the definition of these unit cells with only these points, with these imaginary points. And nature is rather interesting that it only accepts certain type of unit cells in 3-dimensional objects. So we cannot select them as we like. They have a specific shape, but the specific shape we can then determine ourselves. So let's go and see this. So you can see this is a wallpaper. And now we define here, we use these to build up a unit cell. And the idea is now, you can see there's a point here. It's just arbitrary point. I just painted on this. So these are real objects on the wall. And then I went there and put a point there. Now what I do, I add the same points in the exact same positions now. So we started from here. And now you can see in each flower has the similar point here, in there. And now the flower is real, but the point is not, because this is done by me. The wallpaper doesn't really have it. So what I can now do, I will start joining my imaginary points by lines. So let's do this one, that one, that one, and that one. So you can see they form a line, this direction. We're having it. Okay, this is not enough yet. So we have to make the other direction also the connections. So let's start joining these points like this, 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 and this. And now what happened? We sliced the whole physical object into a smaller parts based on imaginary point. So this imaginary point was used, because it's always in the same position, used to create a box where in this box, all the boxes are the same, as you can see. if you look this box, and then you look this box, and then you list this box, they're all the same. So now what it means, when if we want to reconstruct the wall, we need only one box. We just repeat it, we move it in this direction or that direction, we will have the whole wallpaper based on the definition. And this smallest box is here, is the unit cell. But that's not all. We can do, because this is completely arbitrary, we can do also like this. I can join the points in a different direction. And now if you look for this, forget the blue one, but look only the red one, like in here. Now the flower is sitting in a different position of this box, but all the boxes, all the red boxes are the same. So I can also select this one. So the blue one and the red one are the same. So the content is the same. Now I can also make a selection so that I skip one of these points and mark only those points. And now when I repeat it, I will get the bigger box, now this one here, which has the arbitrary position also in the center, not on the corners, but also in the center. But now it contains 2 in there. So you can see the box is 2 times bigger, but it contains 2 flowers. Also with this, I can create the whole wallpaper. So here that is the same as this is the same as this. You have to believe these are also, because you can see only half of them. But that's the case, so we can do this. So the point, selection rules for these things, we call them lattices, later on you will see. So that we always try to make this box so that it has direct angles. So the angle will be 90. We always aim as close to 90 as possible, because that will make mathematically easier calculations. So that's the point. And they don't need to be primitive. So primitive means that you have the point in the corners. And then when this one here, with additional point in here, in the center, we call it non-primitive. So these are the points. But we always like to have it in the corners, but sometimes, depending on the order of the material, we have to have an additional point in there. But that's the idea. So we can do this ourselves. But now imagine that you have to do this for a material which is ordered in 3 dimensions. In 2 dimensions, this is relatively simple, but 3 dimensions, it gets complicated. It's very good that we have computers, because computers are doing this. So now this goes to the concept of the unit cell. So we have to define the unit cell. And the unit cell is, as I pointed to you out earlier, is the smallest repeatable 3D dimensional thing of a volume. Repeating volume of 3D lattice is called the unit cell. And what we do, we need to define it. So it is a box with dimensions. So this is of course logical, because we have a physical object. If we divide it into smaller and smaller pieces, also the smallest box has to have a dimensions. And the dimensions are now mentioned A, B, and C. These are the axes. And then we have agreed the angles between these are called alpha, beta, and gamma. So we have 6 parameters to describe the unit cell. And the idea is there that this is how it looks like. We normally always make a definition that we have a right-handed definition for the axes. Don't worry about this too much, because the computers are doing this. But the point in there is that when we have the idea that A is here, B is there, and Z is there, typically Z is pointing upwards. That's the idea. And then we have the angles. So with the alpha angle is between B and C, beta is between A and C, and then gamma is between A and B. And this is important. All these numbers, all these things, especially these ones, also those ones, are very important. Because with these, we define the possibilities of what is the shape of this unit cell. How can we do this? And here is a nice cartoon of selection rules. So this is the same grid. You can see the same molecules now ordered in there. And now, based on these things, what we discussed earlier already, okay, here's one choice, here's another choice, here's another choice. All these choices are okay. They always have the same information content. So by repeating any of these things, we will get the whole package. But now, agreeing with everything, we always aim to try to select the things so that the angles would be as close as 90 as possible. So here, of course, out of these three choices, that would be our target. So it has lattice points only in the corners, it's primitive, and now you can see all the angles are 90. That would be a nice thing. So A, B, and C alpha beta gamma are called the unit cell parameters, and they are chosen always that they represent the highest possible symmetry of the crystal. Soon you will see how we define it, or the crystal system with the right-handed angles, and angles that are either all about a 90 or higher, or 90 or smaller than 90. And always aim that we would have a 90. So the idea is A along the x-axis, and alpha angle is between B and C. B goes along the y-axis, and beta is between A and C along the z-axis, and gamma is between A and B. It's not so important for you to remember that, okay, which angle is between which axis, because that will be defined later on. But these angles have an impact, because the point is that if we aim to follow these things as precisely as possible, it will then shrink our possibilities to only a certain number. Here are additional, so we could select this one, or we could select this one. They are all okay, but based on the selection rules, we would take the smallest and most simplistic one. Of course, that's real in that sense. And what is there when we are now thinking about the box? So we defined a box only, but nothing what is inside. So there has to be, in a real life, of course, there is something inside the box. How do we tell somebody where is this thing inside the box? And for that, we use atom parameters. So it's a position of atoms. We call it in the reference of the crystallographic axis, the A, B, and C. So the unit cell axis will define us things. And the idea is we call them fractional coordinates, x, y, and z, because these describe fractions of these A, B, and C. So we don't have to give any absolute numbers. When we know the unit cell, only this x, y, and z will tell us where is the atom, where is the coordinate of this atom. So we don't have to worry about this. It simplifies things a lot. So for example, the coordinates of the atom, the center of the unit cell, whatever is the unit cell, if it's small or large, the center of the unit cell is always has coordinates half, half, and half, because it is exactly in the position in the center of the unit cell. And then the point of origin, so the corner, has a value of 0, 0, 0. And then if you go to the other end of it, then it's 1, 1, 1. But now, because it's repeatable, three-dimensional thing, the 1, 1, 1 becomes 0, 0, 0. So everything is described between 1 and 0. So that's the idea. That reduces back to 0, 0, 0, because it's in the next unit cell. And it's a very unique thinking when compared to anything happening in solution, when you have free molecules floating around with no reference. But here we have a reference. We know exactly where individuals, molecules, or atoms are sitting. So the crystallographic coordinates can be presented between 1, 0, and 1, and they're called fractional coordinates. If you are doing molecular modeling in gas state or whatever, then you don't use fractional coordinates because you don't have the reference point. You don't have the unit cell. And the fractional coordinates are only reasonable when you have a unit cell. And then the idea is that now, if we normally do this, we publish the atom parameters, the structure, the lattice parameters must be known. Then the absolute coordinates can be calculated, of course. So we can also describe these as a as their absolute coordinates when we take into account the unit cell. But we don't normally have to think about this, and the computer programs are doing this. So when you have fractional coordinates, you can ask it to print out, let's say, the x, y, z coordinates or mol2 or whatever. So it's automatically done. But in our life, with all the computer programs, the discussions are based on fractional coordinates. So now, how many possibilities we have to select the smallest possible unit? And the point in there is that we have only 7 possibilities for this. And the point is, why is this? Soon you will see, because we have to be able to repeat the same unit cell in all dimensions. And then if they would be different, if they would be badly designed, bad corners, bad axes, they would not fit. There would be empty space, which is impossible. So the point in there is that the first and simplest and the lowest of these boxes is here. It's called triclinic. And this triclinic, A, B, and C axes all are different. And all the angles, alpha, beta, and gamma, all different. So this is the lowest symmetry of these things. And then what we are doing now, we start changing the shape of this by moving first the angles and then also changing the axes. But let's see what happens. So triclinic is the simplest. And then when we go to our, so and then the next one will be so that we have tilted 2 of these angles into 90-degree and one is not 90. Because believe it or not, if you do anything else, it's still the same. So it always goes to that the idea is that you cannot have 2 angles which are not 90 and one is 90, because then it's triclinic. It always can be described by it. But if you want to go higher in the symmetry, you have to fix 2 of these angles to 90. And this is called monoclinic. It's a very common one where A, B, and C are all different. And then alpha and gamma are 90, exactly 90. It's been agreed. Here it's not fixed, but here it's fixed. And beta angle is not 90. So that is called monoclinic crystal system. And sometimes, like it's written here, that sometimes the beta angle is 90.1. And then you will later on see that there is a higher symmetry where all the angles are 90. So there is a possibility that you misunderstand this, or the program can't see, okay, this is not exactly this one, it's the other one. So you have to be very careful when you are doing with the computer program, when the diffractometer is giving you guesses of the space unit cell, you have to be very careful, check that it's reasonable. Could it be something else? Because if you misalign, misselect the crystal system, you can't solve the structure. That's the idea. Okay, we go forward. Then the idea, okay, this is the just conversion of these things. Don't worry about this. But now the next one is that A, B, and C are all different, but all the angles are the same. So we call this system an orthorhombic system. So this is like a box, but in a box, all the angles are 90, but the A, B, and C are different. This is also very common. So in the structures now, the lower symmetry parts are more abundant than the higher things. So the triclinic, monoclinic, and orthorhombic are very popular. The nature likes to pack things in this way. And the point is an orthorhombic. Now, the next step higher from the orthorhombic would be the case where the A and B are the same, but they are different from the C and all the angles are 90. This is called tetragonal. So now we have 2 already, 2 before this, triclinic, monoclinic. Now we have orthorhombic, tetragonal. We have already 4. 3 is missing. Then the idea, we can consider the idea where the system where A equals the same as B, which is not the same as C, and alpha and beta are 90, and gamma is 120. So it's a little bit similar like this, but now the angle is 20. Now it's hexagonal. So this object, because one of the angles is 120, It's hexagonal. It's defined as hexagonal. But in there, we have to define the orientation towards this. So then we say that this is now, the C is unique. This axis is defined because A and B are the same, but not the same as C. And that same also in here. It's a tetragonal. So that's a hexagon. And now we can have a variation of that, which is called a trigonal system, also can call it rhombohedral. And this is easier to describe as a cube, which you have stepped on it. So A, B, and C are all the same. You can see that's the case. But because none of these cases, all the axes are the same. But this is the axis system where the A, B, and C are the same. But all the angles are the same, but not 90. So this is really easily described as a cube. Somebody have stepped on it. So the axis remains the same, but the angles are not. So this is called a trigonal system. So now the final one, of course, which is easy to understand, is the highest possible box what you can create is a cube. And then the cube is A, B, and C, and alpha, beta, gamma is 90. So these are the only 7 possibilities you can organize a box, or let's go to take it this way. These are the 7 forms of a box you can organize repeatedly in 3 dimensions. There is no other form. And this makes, of course, our life much more easier because only what we have to do is to select one of them based on the information what we get from the instrument. But that will come later. And okay, there's this just idea that this is highly symmetric. We will discuss symmetry later on because we have to then know what happens inside the box. We have to know what happens inside the unit itself. But these are, we call them crystal systems. And here is a nice summary of them and some essential symmetry in there. Triclinic, there is no dimensional restrictions, none. And monoclinic, there is none in the axis or the edge, but in angle we have. Orthorhombic, none in the axis, but all angles are defined. And now in tetragonal, 2 of the axes are defined and all the angles are defined, but one isn't. You can see the symmetry is increasing. Trigonal, all the edges are defined, but the angles are not. In the hexagonal, part is defined, C is not, all the angles are defined. And then cubic, everything is defined. But the point in here is that A equals B equals C, it doesn't mean the length is defined. So the length can be anything, but it has to be the same. That's the idea. Like in cube, it means that if the A is 10, B is 10, and C is 10. Or if the A is 100, B is then 100, C is 100. That's, of course, the idea. And all the angles are. So this is the only thing what we have to know now when we think about that we have this box where the lattice points, the additional points are in the corners. And this is actually a trigonal system has a unique feature. It can be described with rhombohedral axes. Again, it's not really important for you. This is done automatically by the computer programs. So it's just a transformation, mathematical transformation done by the computer program automatically, and you don't have to worry about this. The new programs can do this automatically. But it's the idea that you can just have a selection. So this is a hexagonal lattice. You can describe inside that a rhombohedral box. So that is the same kind of a thing to make a selection. Sometimes selecting this R it gives a better, it fits better on the work than defining that as an hexagonal. But anyway, that's the idea. That's the definitions for these 2. But now, remember I was also joining the wallpaper points so that there was a 1 point left not joined with anything. And then it was occurring at that point, it was occurring in it was in the center of the box. And the point is that when we can think about also the idea is that there are additional lattice points than on the corners only. So it is sometimes necessary to choose the unit cell that contains more than 1 lattice point, meaning the corner points. So we need another one to describe the whole thing. So if we don't take it, we cannot have a repeatable thing doing. So that's the point. So then our unit cell that contains only one lattice point, here we call it primitive. And then it's normally marked with P. P is a primitive. But sometimes we have to do it so that we have to select a point, like in here, that there is like additional point. But only with this additional point inside we can repeat that in 3 dimensions. And here we have primitive selections, all these are primitive, and then as I told you earlier, there is one additional point here, then is we call it non-primitive. So if we take this into account, so how many additional possibilities we have in order to put there an additional lattice point will increase the number from the 7. So the 7 basic things remains, but this is like an add-on to the 7 and that's the idea. So for the non-primitive, we call it centered cells, unit cells, and there is only a limited number of ways to choose the cell, and the number of composition possible centered cells, it depends on the crystal system. So now we have 7 crystal systems, and each of them, in theory, could contain additional lattice points like this, but some cannot. So what happens if we take these 2 things into account? Let's see what happens. So it already says here that we can create 14 possibilities, 7 plus other 7, and this is actually what we do. So it is, and then this non-primitive lattice is always larger because it has to contain one of the lattice points, so this one here now. And the point in there is that it has an additional lattice points at the centers or in pairs of opposite size. We can now have a primitive and then additional types. So we have a body centered, which is I. It sits in there in the center. We have a base centered, so it's sitting somewhere on the base. So in this one of these, let's say the walls in here. This is the C. If we call it the C phase, and this is a C phase. And depending on that, it could be a C, A, or B, but now becomes a convention. Because there are these choices which are all the same based on sake of consistency. Somebody 100 years ago proposed that you always use the C for this. We call it C-centered cell. We don't use A and B. It's very not normal. Or then we can have a face-centered F where we have it's in each of the faces. And that is these are the combinations what we can have. So I, C, or F in connection with individual crystal systems. So let's see what happens. The number is already indicated here, but how they look. So all in all, when you do this combination, you will get 14 possibilities, only 14 possibilities. And here they are. So let's start from the lower hand corner. Let's go from the low symmetry to the high symmetry. So we have a triclinic, which is primitive. The red points are the lattice points, and that's the idea. And then in a primitive, we cannot add any more points because the symmetry doesn't allow. So the idea is that if they would be putting something else, it would not be primitive anymore. So we can't do this. But then we can have, in a monoclinic case, we have 2 options. We have a simple monoclinic, so all the lattice points are in the corners, or we have a base, so we can add 1 additional lattice point in one of the faces here now. And then it's typically, as I told you earlier, it's agreed to be on the C side. So this is C-centered. So in the monoclinic, we have 2 options. Now in the rhombohedral, meaning trigonal system, it's very similar like triclinic. We cannot add any additional points in there. So it can only be primitive. So it's only one rhombohedral or trigonal. So now when we go from the orthorhombic case, this will become interesting because in the orthorhombic, you can have that in the corners because now all the angles are 90, but the axes are not the same. We can add 1 additional point in the center, in the body here. It's exactly in 1, 1, 1. No, it's a half, half, half. And then we can also add another version where we have that on the base. So it's here now, typically a C. Or we can have it added in all the faces. So we have in the orthorhombic case 1, 2, 3, 4 possible variations of the orthorhombic unit cell. How do you know which is which? This actually comes from the data. So the information from the crystal will tell us this, that okay, it's better to select a body-centered orthorhombic because this describes the structure better than simple orthorhombic. Okay, in tetragonal we can have two choices because now A and B are the same, so you cannot have it on the face, so you can have it only in the body, in the center. That's possible. Hexagonal is like rhombohedral and triclinic, which is actually only possibility is this hexagonal primitive one. And cubic is the same in that sense, like combination, a little bit like the orthorhombic, but we can have it in the corners, we can have it all the faces or in the center, because here it's all or nothing. So that's the idea. So we cannot have this in here because all the faces are the same. So it has to be only if it's face centered in the cube, they all have to be in the every face. So then we have it in all this, or it could be in the center in the middle. This is a short summary of the same thing. I will not go through, but this is a very nice and simple way for you, and because you will get all the handouts, so then you can repeat and memorize this in there if you need. And this is the same also doing in the summary wise, and here is the primitive or centered lattices. You can see it's now combining all these together is 14. And now only very quickly some presentations for this, how we describe molecules, because the point in there, this is a molecular plots of the same molecule, but now this is how they pack in real life. So now you can start seeing these are ordered. So this is the order of individual molecules in there. And now you can see the order is not the same in all directions. And this depends on how they are organized in the crystal. And this organization here determines the unit cell and determines that is it a primitive or non-primitive ones. And that's that for the first hour. Now we have a break of how long? How much? 5 minutes. We'll have a 5-minute break and then we go on for the next time. So there will be a lot of stuff coming to you now, and don't worry about this because the handouts will help you then going through this material. You have any questions now, so please ask. That I always, because I tend to do this because in the Finnish lecturing course, but students are silent, and maybe they ask during the lecture something. But very often after the lecture, they are very happy, like a stand, what? But then the idea, when you have the handouts, it will help you to understand, because remember, this is building up the story from the really basics. And then it becomes much more relevant when we go further and further. So you might be mixed up now a bit of why so and so, and don't worry too much. Just follow and make notes and then read the handouts. That will be helpful. Okay, let's then continue in 5 minutes.